Hi, and welcome to our archive on higher order derivatives. So our question is, can you differentiate a derivative? Can you take a derivative of a derivative? Sure, why not? Generally because when you get a derivative, or when you take a derivative, you end up with another function. And as long as that function is differentiable, you can take a derivative of it. Okay, so let's take a look at some notation first. If you've got your notes out, we use the notation f prime of x is the first derivative, right? So if we take the derivative of f prime, we call that the second derivative, and it is noted or denoted by f double prime. So f with two apostrophes there. So we read that as f double prime, or the second derivative of f. And so you might see in mathematical notation d dx of f prime is f double prime of x, or d dx of dy dx is d squared y over dx squared. So notice where the squares go when you use that dy dx notation. And then, of course, we could take a derivative of the second derivative. And if you do that, you get the third derivative. You could say f triple prime, or you can just say the third derivative. So again, the notation would be d dx of f double prime is f triple prime, or the third derivative of x. Or you would see it as d dx of d squared y over dx squared is equal to d cubed y over dx cubed. Now remember, these aren't truly squares and cubes, it's just a notation. So you could say is d to the third y over d dx third, or dx to the third sort of idea. Okay? You could continue differentiating. You could take a derivative of a third derivative to get a fourth derivative, and then a fifth derivative, and so on. But essentially, once you get past the third, we change our notation a little bit. If you're using the dy dx notation, it really doesn't change. You just replace the 2 or the 3 with whichever. Oh, let me try that again. Replace the 2 or the 3 in the dy dx notation, like d squared y over dx squared. Replace the 2 with, say, the fifth derivative. It would be d to the fifth y over dx to the fifth. And when we're doing function notation or just y notation, what you do is you put the number in parentheses. So here we indicate the fourth derivative would be f to the 4 in parentheses. Now that's to distinguish the fourth derivative of f from f to the fourth power. So we don't want to mix those up. So that's why the derivative is put into parentheses to indicate it's different from f to the fourth power. It's the fourth derivative of f. So let's practice finding some higher order derivatives. It's really not that difficult. You just need to keep track of where you are. Okay, so let's go to the eBoard and try these out. Okay, the first problem we're given is the function f of x is equal to x to the fourth minus 2x cubed. And we're asked to find the first derivative, the second, and the third derivative. We'll find that we have applications for these first and second derivatives, and specifically that we'll find when we start to analyze graphs of functions, that they'll tell us some information about the function, whether it's increasing or decreasing function, whether it's curved up or curved down. These derivatives will give us information about that. All right, so let's try. First derivative, pretty straightforward and easy. At this point, you should have no problem doing a derivative of x to the fourth minus 2x cubed. So using the simple power rule, that would be 4x to the third minus 2 times the derivative of x cubed would be 3x squared. So the first derivative is 4x cubed minus 6x squared. Okay. Second derivative is the derivative of the first derivative. So that would be 4 times the derivative of x cubed, that would be 3x squared, minus 6 times the derivative of x squared, so that would be 2x. So 12x squared minus 12x is our second derivative. And then, of course, our third derivative. And again, you can use the parentheses notation if you'd like to, as I've shown here on the whiteboard. So that's going to be the derivative of our second derivative. So in this case, that would be 12 times the derivative of x squared, which would be 2x, minus 12 times the derivative of x, which is 1. So this is 24x minus 12. So those are our three derivatives. Our first derivative, our second derivative, and our third derivative. So pretty straightforward. Just taking derivatives of the result of your first derivative and then derivative result of your second. So let's try another one. In this particular example, they're telling us this is the fourth derivative. So they've done some work along the way to find the fourth derivative, and the fourth derivative is x plus 1 to the second power, and they want us to find the sixth derivative. Okay. Well, in order to get to the sixth, we've got to go through the fifth. So that's the first thing we need to do. Fifth derivative of x is the derivative of the fourth derivative. Okay, so here's where we're going to use our chain rule here, which is going to be, we're going to take the 2 and bring it down. So remember, we've got inside in blue and outside in red. So outside first, bring the 2 down, leave the inside alone, subtract 1 from the exponent, and then multiply by the derivative of the inside. So that would be 2 times x plus 1 times 1, or just 2 times x plus 1. So then the sixth derivative would be the derivative of our fifth derivative, which would be, let's see, constant multiple, bring the 2 down, comes along for the ride, right? We'll just rewrite constant multiple, and then times the derivative of x plus 1, which is just 1. So our sixth derivative is 2. Okay. So generally, our problems are going to fall into one of 2 categories. You're going to be given the original function and asked to find the second or third or fourth or fifth or sixth derivative, whatever. And the other form is they will tell you you're already at the, say, second or third, or in this case, fourth derivative, and then to find a further derivative down the line. In this case, they gave us the fourth and asked for the sixth derivative. You also find in your textbook some other applications for derivatives. For example, you might see applications with respect to position, speed, and velocity, those sorts of things. As we get into further chapters and further sections, you'll see more and more applications here for higher order derivatives. Okay. And that is pretty much it for this section. And as always, if you have any questions, don't hesitate to either post them to the discussion board or send me an email.